So in this video I'd like to introduce you to two other types of infinite series. We've looked at infinite geometric series. The series that I have here certainly isn't geometric, it doesn't have the look of that. And what we want to do is decide if it converges or diverges. So since we don't know what this is, it's probably a good idea to write out some of the terms. So if k was 1, our first term would be 1 over 1 times 2. Our second term at k equals 2 would be 1 over 2 times 3. Plus k equals 3, our next term would be 1 over 3 times 4. And I think we can see what's happening here. Getting a series of that form. So this is adding together a half, plus a sixth, plus a 12th, plus a 20th, and so on. And when we're wondering whether it converges or diverges, remember we're looking at the sum of 2 terms, the sum of 3 terms, the sum of 4 terms, the sum of n terms, and then taking n to infinity, looking at whether that sum gets closer and closer to some fixed value. Well, just to get an intuitive feeling as to whether this converges or diverges, first of all, a couple things. I noticed that my terms, each of the terms in the series is getting closer and closer to 0. So that's a good sign. If I'm adding on less and less each time, a number closer and closer to 0, there's a chance that my series may converge. But that's not enough to know for sure whether it does or not. Another thing we can look at to get a feeling for this is my calculator. And on my stat menu, I've got list 1 set up as 1, 2, 3, 4, 5 just to list the term number. And in list 2, I just want to have listed the terms of the sequence. So let's type this formula in. So up to L2, and if I go to second function stat, which is the list menu, over to the sequence button, I'll put my expression in for this, 1 over, in brackets, k times k plus 1, n is the variable, and let's do the first 20 terms. Paste our formula into L1 and press enter, and we generate the terms. So the first term is a half, my 1/6 is term 2, my third term is 1/12 as shown. Now what we want to do is we want to look at the sums of 2 terms, 3 terms, 4 terms. In other words, we want to see the sequence of partial sums. So in list 3, I'm going to do second function list, ops, cumulative sum of list 2. And so the first 2 terms add to 0.666, the first 3 terms add to 0.75, the first 4 terms add to 0.8. And as n gets bigger, by looking at this sequence of partial sums, I can get a feeling as to whether I think the sums are getting closer and closer to some value as n gets closer and closer to infinity. Well, seems like maybe we're going towards 1. Let's look at this from another point of view. Let's use our sequence graphing button. And remember, if I want to graph the sequence of partial sums this way, I've got to do so as a recursive formula. And my recursive formula means that I take the previous term, u n minus 1, and I will specify the first term in a moment, and I add on the value of the next term, which is 1 divided by n times n plus 1. And my first term is a half. So if I look at my table for this, I'll notice that these values are the same as was appearing in list 3 earlier, the sequence of partial sums. If I look at it graphically, I can see that as n approaches infinity, it seems like my graph is approaching some fixed value. Looks like it is approaching 1. Alright, so these are all intuitive ways to try to get a feeling for whether the series, the infinite series, diverges or converges. We're having a feeling that it's converging to 1. And now we want to do this analytically. Now, how are we going to do that? Well, what we're going to do here is take this series, and by the way, you see the term telescoping series up here. I'll talk a little bit in a moment as to why this is called a telescoping series. But what we're going to do is we're going to take our sequence expression and we're going to break it up as the sum of two fractions. So we're going to use the approach of partial fractions that we used earlier with integration and try to break this up into the sum of two individual fractions. What I'm going to do is multiply both sides by LCD, which is k times k plus 1, and that would give me 1 equals a times k plus 1 plus b times k. And remember, the strategy here is to equate coefficients. So let's expand the bracket. And we've got terms with k, and we've got terms with no k to the 0 exponent if you want to think of it this way. And so we think of our 1 as 0k plus 1 equaling, let's factor the k out of this. That would leave us with a plus b times k plus a. And then equating coefficients, 1 would have to be a, and 0 would have to be the value of a plus b. So a plus b would have to be 0, and since a is 1, b would be negative 1. And I can then plug these values now back into a and b up here, and so I've broken my original sequence expression down as shown. So let's put this all together. What we've just done is we've taken our sequence that looked like this and said, well, that's equivalent to this. Alright, so the question is, why did we do that? Well, what we're going to do now is we're going to write out the terms of the series using this form of our expression. So here we go. If k is 1, our first term would be 1 minus 1 over 2. If k was 2, this is k equals 1. If k was 2, our next term would be a half minus a third. And our next term would be a third minus a quarter. That would be if k is 3. And this is going to go on endlessly. Now I think you can see what's going to happen here. If I remove the brackets, and I can do that since I'm just adding, this and this is going to cancel, this and this is going to cancel, and what I'm going to be left with is the first term and the last term. But if I take this to infinity, there will be no last term, and so this is all going to approach 1 in terms of infinity. But let's just go a little bit slower on that. Let's just back up a second. Let's first write our infinite series in terms of the corresponding finite series. In other words, there's an endpoint. So if I were to want to get an expression for the sum of n terms of our series, I can see that, for example, if I were to stop at 3, that my result would be 1 minus a quarter. And so if I were to stop at n terms, my sum should be, since all the intermediate terms are canceling out, the first term minus the last term. And I can see that my last term is a quarter if k is 3. So if k is n, my last term would be 1 over n plus 1. And this is our sum of n terms. And the reason I've written all of this in this way is because remember that when we're asked to decide if our infinite series converges or diverges, that means to look at the limit as n goes to infinity of our sum of n terms. And since our sum of n terms in this case was 1 minus 1 over n plus 1, let's evaluate this limit as n goes to infinity. 1 over infinity will be 0, and this will equal 1. And if our limit converges, that means that our infinite series converges to 1. So our series converges to 1. In other words, the sum of an endless number of terms is equal to 1. Now, by the way, this particular type of sequence that I've demonstrated here is called telescoping. Now, telescoping series can come in all sorts of different forms. They're not necessarily as easy to identify as geometric, but the whole idea is that the intermediate terms in it cancel each other out. And so you're left with a first and a final term, and by taking a limit, you can therefore find the value that the infinite series converges to. Let's look at another type of series called a harmonic series. And a harmonic series is of this form. And in sigma notation, that can be written as so. So the question is, does this series converge or diverge? Now, before we look at this analytically, let's go to our calculator. To enter it recursively, I take the previous term and add the value of the current term, but I need to specify the first term. There is a graphical representation of my sequence of partial sums. Let's look at the table. That might help us a little bit more. Does it look as though our sum is approaching some fixed value as then gets larger and larger? Well, it looks like it's continuing to grow, but I'm not completely sure about that. So let's look at this a little bit more analytically. So I'm just going to write my infinite series out with a few more terms. 1 plus a half, etc. And what I'm going to do to make my argument is I'm going to group terms together like so. So in this series I have 1 plus a half plus, now I'm just going to take these two terms and come down here. 1/3 plus a quarter. I know that's going to be more than a quarter plus a quarter. And this a quarter plus a quarter I know is a half. So what we're saying is that these two terms here, just on their own, add to more than a half as it is. So I'm going to put greater than a half. Okay, I'm going to do the same kind of argument with these next four terms. A fifth plus a sixth plus a seventh plus an eighth, that would be greater than if all of these were eighths. An eighth plus an eighth plus an eighth plus an eighth. These together would be a half. And so this we know is going to be more than a half. So again, these four terms here I could replace with adding a number greater than a half. Now, if you keep taking more groups of terms, like 8 together, the next 16 together, you're going to end up seeing that what this series can be thought of as 1 plus a half plus a number greater than a half plus another number greater than a half plus another number greater than a half. And so I think you can see that this series is going to diverge because I'm continuing to add on at minimum a half, but actually more than a half for every group of terms. And so there, based on that argument, we say that this series, which is the harmonic series, diverges. So whenever you see this particular series, you need to recognize it as a harmonic series and know that it diverges.